Hello, welcome to this MEI M1 revision video. We're going to be looking at June 2010 question 8. This is one of the longer questions towards the end of the paper, so let's just have a quick read through the question first. So we've got a cylindrical tub, mass 250 kilograms on a horizontal floor, and we're told that the only resistance to motion is friction, all of the resistance is negligible. And the first attempt to pull the tub, which we can see here, is a horizontal force of 150 newtons in the I direction, and this is a plan view from above. So we firstly have to calculate the acceleration if initially we ignore friction. That's 2 marks. And then we go on to improve the model by saying that there actually is friction, the tub does not move, and we have to work out the magnitude and direction of the friction that is opposing the pull. We then go on to a slightly more complicated situation where 2 more forces are added, and there's a second attempt to move the tub, and we can see here that there's an angle theta. Theta's acute, and the resultant of the 3 forces is in the I direction. So we have to determine the value of theta and the resultant of the 3 forces. Once we've got that resultant force, we're told that the tub moves with a constant acceleration. It travels for 1 metre from rest in 2 seconds, and we have to show that the magnitude of the frictional force acting on the tub is 661 newtons. That's 5 marks. To finish off, a final 5-mark section, when the speed of the tub is 1.8, it comes to a part of the floor where the friction on the tub is 200 newtons greater, so that's on top of the friction that's already in place. Pulling forces stay the same, and we have to work out the velocity of the tub when it's moved a further 1.65 metres. And again, it's another 5 marks. So let's start with part 1. So we have to calculate the acceleration of the tub if friction's ignored. Well, using Newton's laws, we can say, using F equals ma, that 150 newtons in the direction of I will be equal to the mass, 250, times the acceleration. And therefore, the acceleration must be 0.6 meters per second squared in the I direction. Moving on to part 2. It says, in fact, there is a frictional force and the tub does not move. Write down the magnitude and direction of the frictional force opposing the pull. Well, the frictional force only needs to overcome the forward force. And so the frictional force will in fact equal the pulling force of 150 newtons, but will oppose motion. So it will be in the direction minus I, so it'll be in the opposing motion. 2 more forces have now been added in an attempt to move this tub. We have to determine the value of theta and the resultant of the 3 forces. Now it tells us that the resultant of the 3 forces is in the I direction, the I direction being horizontally forwards. So it's telling us there's no motion in any other direction, and in particular there's no motion vertically as we look at this diagram. This is a plan view, so that would actually be left to right. There's no left and right motion. It's all going forwards, there's nothing to the left and there's nothing to the right. That must mean that the component of this 300 force and the component of this 450 force that go from left to right must be equal. Now, if we have a look at the component of this force vertically, we know that that would be 300 sine of 40. That would move the tub to the left. And then we know that the 450 Newton force would have a component of 450 sine of theta. And those two would have to be equal. The motion to the left and the motion to the right have to balance out, otherwise it wouldn't keep moving in the direction I. So rearranging this, 300 sine 40 divided by 450 equals sine theta, and so theta will be the inverse sine of 300 sine 40 over 450, which works out to be 25.373 degrees. You could round that off at this stage, but I think we're going to need it in the next part, so I'll keep the full value there. So we've determined the value of theta, it's around 25 degrees. Now we have to find the resultant of the three forces. So I'll go on to the next page to do this. So we're going to have a component of the 300, we'll have the 150, and we'll have a component of the 450 as well. So in the I direction, we're going to have the 150 that we started with. Then we'll have 300 cos 40. And we'll have 450 cos of that theta angle that we've just found. So we'll just flip back to the diagram. You can see it's cos for both of those two, and then the 150 is already in the I direction. So if we work that out, that works out to be 786.401. And so rounding that off to 3SF, that would be 786 newtons in the I direction. So that's part 3 completed. We now move on to part 4. It says, with this resultant force, the tub moves with a constant acceleration and travels 1 metre from rest in 2 seconds. So let's just jot down the resultant force that we got in the last part of the question, because we're going to need it here. So keep that in your calculator. And we also know that it's travelled 1 metre from rest, so U is 0, in 2 seconds. Now what we need to know is the acceleration during this phase of the motion, because we need that for our subsequent calculations. So using those, we can see that we're going to be doing suvat, and S equals ut plus a half at squared is the one to use. So S is 1, U is 0, so that first part is 0. We don't know A, and t squared is 4. And rearranging this equation, A works out to be a half. So now we can start to calculate the magnitude of the friction acting on the tub. So we know, using F equals ma, F is the resultant force, so we have 786 newtons approximately pulling the tub forwards. There is a resistive frictional force, and that will be equal to the mass multiplied by the acceleration. So, typing this into the calculator and rearranging, we'll have 786 minus, bringing this over to the left, that'll be 125. That will equal the frictional force, and if you work that out, the frictional force works out to be 661.4017, and so it is indeed 661 to 3SF, as we are required to find. So that's part 4, and then the last part, again another 5 marks. The speed of the tub is 1.8, so let's jot that down. That's the current speed for this phase of the motion. And it says we need to find the velocity of the tub when it's travelled a further 1.65 metres. Now we don't know the acceleration because there's an increased frictional force, and the velocity is the thing that we need to find. So acceleration we're not sure of, and velocity is the thing that's given in the question. So we're going to have to find the new acceleration. Now the frictional force on the tub is 200 newtons greater than what we started with. So we're going to have the same kind of equation as the last part. We've got the forward forces, they stay unchanged. The question tells us that. We've got the frictional force we've just found in the last part of the question. And then we have an additional 200 newton force. Notice it says the frictional force is 200 newtons greater, so that's on top of what was already there. And we know that will be equal to the mass multiplied by the acceleration. So using the full values if you can there, and then divide through by 250, we get an acceleration of minus 0.2999 recurring, which could round off to minus 0.3. So that will go into our equation here, and then we can see we're going to be using v squared equals u squared plus 2as. V is the thing we want to find. U, we know, is 1.8. 2 times A times S. Substitute those in, and we get V squared equals 2.25. And so, taking the square root, V will be 1.5 meters per second. Okay, so that's the end of the question. Let's just have a quick look now at where the marks are allocated. So let's go back to where we started from. So part 1, using F equals MA, a correct method there for using that, and an accuracy mark for the correct answer. So that was quite straightforward. For part 2, we've got 2 B marks. The first B mark is for saying that the frictional force would be equal to the pulling force, so in other words it's 150, and then a second independent mark for saying that it's in the opposite direction, so indicating that it's in the direction of minus I. Moving on to part 3, we have a method mark for writing down that these 2 components of the forces, left and right, would be equal. And then you get an independent method mark for getting either of those 2 correct, so either the one on the left or the one on the right, and then you get an accuracy mark for getting round to the final angle. So that's the first 3 marks. Moving on to the next page, we get a method mark again for attempting to resolve the forces in the I direction. You get an accuracy mark if you get at least one of those 2 resolutions correct, and then an accuracy mark for getting down to the correct final answer there. Moving on to part 4, we get a method mark for attempting to use SUVAT, and for an accuracy for correctly getting down to a half. And then F equals MA, using this method resolving the forces, gets us a method mark and an accuracy mark for correctly substituting in your values. So your value of 786, for example. You then get the final 5th mark here. It's an explanation mark for correctly showing that your calculations do indeed round off to 661 to 3SF. So make sure you show that final step. And then going on to part 5, we first of all get a method mark for correctly resolving to the right hand side, and you get a follow through mark if you use your values here to get down to an acceleration. We then get a method mark for using SUVAT, another follow through mark here for correctly putting the values in the right places, following through your own value, and then a final accuracy mark which must be correct. On the mark scheme, CAO means correct answer only. So that's the 5 marks for that part of the question. If you'd like to look at any of the other revision videos, go to our website www.furthermaths.org.uk.